First of all, I want to thank the organizers for inviting me to give me the opportunity to speak here. Actually, to be honest, I learned about this event from organizers. But now when I see all this, I'm very happy that something like that exists. But I want to make one remark. When Victor offered me to make a talk here, I wasn't actually sure whether I should accept the invitation or not. I used to do the last couple of years quite technical mathematical talks, and I wasn't sure whether I can pull these talks up so that it's kind of give you some top enough view for a broader audience, and still enough details. It doesn't make the talk trivial. Let's see whether it worked out or not. Since I thought I'm gonna speak to computer vision people, I thought that maybe it's a good idea to put some images to the slides. Yeah, but seriously, that's what I wanted to call a motivation for my talk. Indeed, don't believe me, I have another motivation. But anyway, these are the applications I worked on, like on a recent, maybe 5 years. I believe it's readable. So the 3D reconstruction, optical flow, you know what's that? For the 3D reconstruction, you have a couple of cameras. You want to estimate the depth on the scene. Optical flow, kind of dual problem. So you have a single camera and some moving objects. You want to know how they move. That's a nice application, 6D pose estimation from robotics. You have a robot, and the robot should grasp some object. And of course, if you want to grasp an object, you have to know where the object is. So 3D coordinate in the space, but also quite useful if you know how the object is rotated in the space. So if you know you have a chair, you want to carry it somewhere, then you know how to grasp it. If it's staying or it's lying or whatever. Yeah? In that sense, that's 6D pose, so 3D coordinates in the space and 3D rotation in space. Segmentation probably you don't need to explain here. That's like three kind of classical problems in computer vision. And I also like very much to work on bioimaging applications, which are in a sense kind of mid or long-term applications, which biologists are interested in. And just two examples of that are self-segmentation annotation. So here you see this nice worm. It's a C. elegans, how biologists call it. Anyway, it's just a sequence of characters, you know, C. elegans. Why it's elegant. But say 5 people, 5 years, that's quite a prototypical organism, and 5 people, 5 years worked on creating a map of the cells of this guy based on images and observations. So you can multiply, say salary 100,000 euro a year, times 5 is 500,000, times 5 years is a couple of millions for just creating a single atlas of this guy. And that's just one stage of the development stage of this organism. It has like 10 different stages. And at a small stage, it has only around 500 cells there. And if you go then to 1,000 cells, you probably need 50 people and 10 years, or 20 or 50 years. And it's going to be astronomical numbers. Yeah? So you want to do it automatically, of course. Another classical problem is self-segmentation tracking. So if you think about computer vision, tracking is a typical problem, but the difference here is probably the cells are looking very similar to each other. So the cells are kind of, you can't distinguish one from another, typically, and they are also used to divide, you know, to develop. What you want here, you want to track the parts of the living being, where they come from which cell at the beginning. Good, that's it. I don't have images in my slides anymore, sorry. Okay, it's a joke. All these problems or applied problems, if you want, have a similar structure, namely, you know where I started? Like 5 minutes ago, let's say so. Yeah? Similar structure, so they consist of many small parts. What does it mean if you think about computer vision problems? The small parts are just image pixels. If you think about cell tracking notation, typically what you get as small parts is just hypothesis or over segmentation of the image. So you get, in principle, you try to find the cells of the image, but you don't try to find exactly where they are. You rather generate more cells than you need at the end. And after the tracking, you can decide whether the segmentation is correct or not, or which segmentation is correct or which not. These parts must be labeled by a label from a finite set. You know, we are starting speaking mathematically, finite set. It's and in 3D reconstruction, these are just depth levels from 1 to n. In a segmentation, it's like segment level, it's car, road, pedestrian, etc. If you're thinking about cell detection or tracking, it's just 0-1 decision. Either it's correct segment or not. And moreover, these parts are mutually dependent. Yeah, if you think about 3D reconstruction, you realize that the disparities or the depth in neighboring pixels should be similar. Otherwise, you get a noise at output. So what you typically see is like, mathematically speaking, piecewise continuous scenes. If you think about segmentation, then two neighboring pixels probably belong to the same object, much more probable than to different. Cell regions, segmentations, are not allowed to intersect with each other. The cell at time t might be close to the cell at time t+1, and so on and so on. Well, depending on the problem, depending on the application, you can formulate different optimization problems, combinatorial optimization problems. And these kind of properties lead to different optimization problems. I will be speaking about one particular one, which is probably in this community have the longest history. Was studied long enough, and for me it plays a role of a test bed for new methods. If I have some new ideas, I try it on this problem, and then think how to transfer this to problems with different structure. So this problem has different names, different communities, not only computer vision, machine learning, but also communities have nothing to do with vision or machine learning. In our community, it's used to call discrete energy minimization, or map inference, maximum posteriori inference for discrete graphical models. There are also other communities where it's called, or very similar problem is called weighted or valued constraint satisfaction problem. That's everything more or less in this domain. And I formulate this problem now. I hope I don't scare you. So the problem is given a graph, and you have this rectangle such as node of the graph, and these lines here between the rectangles are edges of the graph. You associate with each node of the graph a finite set of labels. Yeah. So the nodes of the graph are just objects, and the edges of the graph denote that these objects interact with each other, or parts of the object, they interact with each other. The labels denote the states of each particular part. You may think about labels such as just depth levels, if you think about stereo construction. And each label is assigned a cost, or probability, or weight, whatever the name you like. I like to speak about the cost because I want to minimize the cost. Yeah? You'd like to maximize the probability, but minimize the cost. And moreover, you have a cost assigned to each pair of labels in the neighboring nodes. So all these lines here just denote that there is a cost sitting between these two labels. And what you want actually, you want to assign a single label in each node of your graph. Yeah, single label in each node, such that the total cost, or total cost sitting in the labels, I call them unary cost, and total cost sitting on the edges here, the pairwise cost, should be as small as possible. Yeah. If you think like very quickly what does it mean? It means you have, say, 100 times 100, 10,000 nodes. It's a very small image, and you have, say, 100 levels of depth levels, which means 10,000 times 100 is just 1 million. Oh, wrong. So you have 10,000 in the power. No, 100 in the power 10,000. Yeah? All possible configurations you want to find out. So it's definitely not possible in like a breakthrough manner. So you have to do something with that. We are in the area of combinatorial optimization, which means the problems can be easy, can be difficult. This one is very difficult and be hard. So you can forget about having a solver for that for all possible cases. So everything I was speaking about, it's typically all examples come from computer vision or bioimaging. I'm not responsible for any other area. Everything what I'm speaking about may happen that it doesn't work there. Yeah, and the time I'm working in this area at least for the last 10 years, and in the recent couple of years I started to build a slide, why not neural networks? Yeah. There are a couple of reasons for that. First of all, such models allow you to easily incorporate prior knowledge about your problem. Now what does mean prior knowledge? It means, you want what you want to reconstruct. You want to incorporate the knowledge how you're in a 3D reconstruction, how your surface should look like, or what you expect to see there. It implies that you need less training data, which is expensive, training data. It implies that you can do faster learning because you have less data. At least, it implies that you guarantee that the result of your reconstruction satisfies the conditions, your prior conditions. Oh, second point is kind of discussable. This model is computationally cheaper. Discussable in a sense when it starts thinking about NP-hard problem, which is, there are no polynomial solver, but they are cheaper if you start thinking about neural networks as hundreds of layers with dozens of GPUs, which work for increase the entropy of our planet couple of weeks. That's much cheaper. And the last point, which is actually motivation for me, is the mathematical transparency of these models. So, I'm doing something here, I know what I'm doing. Yeah. Good. Okay, saying that, I don't say that neural networks are not unuseful. Actually, I believe they are quite useful. But they are useful for modeling for creating such combinatorial problems. So basically, they are useful. If you have a model or a problem with some costs, we need the costs, unary pairwise costs. We have to take them from somewhere. We can, of course, do it manually, play with that. It's nice work, but it's not interesting that much. So what you actually want to do, you want to train this costs, and that's where the neural networks actually can give quite nice and important input. So just for simple understanding, what's the difference between just pure neural network and neural network plus optimization problem on top of that, what the pure neural network would do, you would run it, and afterwards, in this graphical model, you would just independently in each node select just the best label. That's your solution. Instead, you try to solve much more complicated thing here, and you believe that the results get much better. We have this direction have become kind of popular recently. We also wrote an overview paper about existing methods here, and now it's already outdated. It's often in such hot areas. But if you don't believe me, it's important. It really works. I just have stolen a couple of pictures from the paper of my former colleague Savchynskyy, with whom I started 20 years ago, working in the key in the lab, guidance of Professor Schrödinger, our work. And look here, that's an image from the new Mittelber dataset. That's a CNN, but very, very shallow. 3 layers and 7 layers. That's the output of stereo construction you get here. Yeah? If you just add on top of that, of this simple, stupid CNN, small CRF, I call MRF, so graphical model we just talked about, you get somewhat better result. But if you train this model, CNN and CRF together, your result becomes much, much better. So to give you some numbers, Kitty dataset, CNN3 has a huge error, so the smaller number, the better. So that's a huge error. That's a state-of-the-art method back to that time. Yeah, just adding just a CRF on top of that, you are getting you decreases error significantly. If you do add it to 7 layers, then you're almost in the state of the art, or you beat the state of the art here. Yeah? And if you add this CRF to the state of the art network, which is much more layers than 7, you get even better result than state of the art. Quite impressive. At this point, some of you could raise a hand and say, why? I don't believe you. Why don't everyone does it? If it works like that good? And the answer, in a sense, a bit sad. The answer is that because there are just few people in the world which can solve these problems as fast as Sasha Shklovtsov can do. Good. I believe there are a couple of challenges also for this problem. I just listed here. I'm not sure whether it's well visible here. So the key component are fast parallelizable large-scale inference for the combinatorial problems. The second challenge is actually, I will be speaking about particular problem, but there are a number of them which are interesting for the computer vision community and machine learning. And this one is most developed, and for others, the methods still have to be developed to be interesting for the community. Some technical questions. If you think about combining the combinatorial solver with a neural network, roughly speaking, almost the only method, I wouldn't say only, but almost the typical method how you train these boxes, you differentiate through, and you think how to differentiate or you use some stochastic gradient algorithm. And if you think how to differentiate over a combinatorial solver, that's getting not trivial, because the combinatorial solver just gives you the output out of a finite set. It's not even differentiable. It's not even continuous function. There are a couple of methods how to do that. It's not a new question. It's solved in a sense, but I believe there is still something to do in that direction. Well, my talk is on. I will touch only this question here, and not in all details. I just show you a couple of questions what is important here, how to build efficient solvers here. It's not everything in the direction. It's just a small piece of the big mosaic. The outline of my talk is basically consists of 2 parts. The first part is Lagrange dual problem. So you may say, could you use some understandable words? And understandable words means actually I'm not going to solve this NP-hard difficult combinatorial problem. I want to approximate it, and Lagrange dual is just the way how to construct a very powerful approximations. But this approximation are already polynomial solvable, and you can do something quite efficient with them. And afterwards, I will consider this problem and answer a couple of questions on the way how to build an efficient solver. Well, again, recall what we learned already 50 minutes ago. Okay, graphical model, so graph, nodes, which are parts of the objects, and labels are states of the objects, things about depth levels here. Well, I was thinking kind of quite some time how to introduce this mathematical notation, so mathematical formal things as easy as possible. And probably the simplest way to introduce the Lagrange dual is based on the representarization or equivalent transformation of the problem. So we are going to minimize this function, and this function depends on the unary and pairwise costs. But at the end, the number we want to minimize is the total cost of the labeling. So total sum of these numbers. It turns out we can construct other numbers, such that the sum remains the same for each labeling. How to build these numbers? Yeah, well, if you consider a cost of a single label and can subtract a number from that, and add the same numbers to all pairwise costs attached to this label, you don't change the cost of any labeling, because any labeling either contains this label or not. If it doesn't contain, you don't change it because it doesn't contain none of these pairwise costs. If it contains it, it contains exactly one of these pairwise costs, so you basically subtract the same number. okay, yeah. Of course, if the cost of any labeling is the same, then the minimum is also the same. And now you do a simple trick. You say, well, instead of minimizing the sum of values, I just sum the minima of the values. And of course, you get the number which is smaller. Well, what does it mean? A bit more details. If you try to solve the problem itself, what you do, you try to find the labeling. Say, imagine your graph is just 2 nodes and a single edge. What you want to do, you want to find the best triple of the cost of one label on the left, label on the right, and the pairwise cost between them. Yeah? The dual problem says, well, it's too complicated, it's too difficult, you know. So we do it differently, we do it a simple way. We find the best label on the left, the best label on the right, and the best pairwise cost, which need to connect them. Yeah? Well, so for any this numbers phi, so which I just introduced here on this slide, they're called reparentrization. It's a Lagrange dual variable, the number of names of them for them. So I call them reparentrization. And in a sense, the dual problem says, for any of these numbers phi, we get the lower bound. What we want to find the numbers phi, so we want to reparentrize. We want to shift the cost from the pairwise to unary factor, from the edges to labels and backwards, such that this bound, this lower bound, is as high as possible. Yeah. It's a small slide, which is reminiscence of the technical talks I gave recent couple of years. If I explain this in the specific manner, people start thinking, wow, that's something very specific for this kind of problems and can be generalized to other optimization, whatever problems. So how are we going to work with that? And that's answer to those questions. So most of the combinatorial problems which I work with, or many of them, can be formulated as integer linear program. Integer linear program is minimizing a linear function over the polytope P intersect with 0, 1 and dimensional cube, and n is say 100 times 100. Yeah? And you assume that the polytope P with some constraint x equals 0 is kind of difficult to solve. But if you would remove this constraint from here, the problem becomes easy. What you do then, the Lagrange relaxation in general, says, well, move this constraint to the objective of your problem with and multiply it by a vector phi. That's exactly the reparentrization we are speaking about. And then if you do some elementary linear algebra, you will get the cost vector times x. And this cost vector is nothing but a reparentrized problem we are speaking about. So transform problem such that as soon as x equals 0, so you have the visible point here, of course this guy disappears, and it means the cost of the labeling is the same as the cost of this labeling. So that's kind of more general mathematical notation which you can use basically for any for a large class of combinatorial problems. What does mean these constraints? What these constraints actually mean, particularly here? This constraint say basically that if you select the optimal label left and the right, and optimal label pair in the edge, so they have to match to each other. So the situation should look like that and not like that. Yeah? Oops. Well, that's a bit overview slide. What you get at the end, that's a Lagrange dual problem. Speaking mathematically, it's a concave, non-smooth piecewise linear problem. And the key word here is also large scale. So it contains hundreds of thousands or millions, sometimes even billions of variables. And although it's just concave problem, you probably have learned, every one of you know that concave is the same as convex in a sense, and convex problems are solvable. It's not that easy to solve due to this huge number of variables. So but still there is a zoo of methods which were developed for such kind of problems. This is so-called first-order optimization methods, starting from block coordinate suggested in the 50s, and specialized in a solver developed in the 70s by Professor Schlesinger and colleagues. Then Subgradient methods, one of the simplest methods which guaranteed solving this problem, at least in theory, developed also in Kiev in the 70s in the lab of Noam Shor, Professor Shor. And then generalization of these methods, bundle methods, other methods, proximal methods, example from again 70s years. Afterwards, relatively new smoothing technique, which first smooth this function and apply then usual kind of gradient-based techniques and so on and so on. For all this, there are some literature, like general literature, you know, the newest tools are from 2000 something, but most of the methods are quite old, quite ancient. And still all these methods have been already tested on this particular problem. Yeah, so one of these, okay. The question which I actually going to answer in this talk, or not going to basically towards answer this in this talk, is they are the best method for such kind of problems. Yeah? To do so, I don't have time to go into details of all this zoo, and in a sense, what I just believe me here that these methods can be divided in two classes. One class is subgradient based. With a representative subgradient, the most simple and probably the worst working one out of this family, and the other method is block-horn ascent method. Yeah? So this slide gives you like very rough, high-level introduction. What are these methods? What are these methods? Yeah? So subgradient looks pretty much like a gradient ascent. So remember, we are optimizing the concave function, so we want to do ascent, not descent, as in the case of convex optimization. Our variables are just representational phi, yeah? And the representation phi on a t+1 step is just representation phi on t step plus the step size. If you work in machine learning, people used to use the word learning rate. Okay, step size. And this fancy notation here, in a sense, is a subgradient of the function d of the dual of the Lagrange dual. You can, if you don't know what subgradient is, you may think you can think that you just do a gradient ascent. In a sense, if you work with neural networks, you also do subgradient, but to avoid explanation what's the difference, people call it like gradient. You know? Good. This very simple method, given the certain technical constraints for the step size, have a nice properties. It guarantees that you converge to the optimum of this dual function, and moreover, even convergence speed of this kind of methods. And it holds not only for the plain subgradient, but also for all improvements on top of that. Another group of methods are block-horn ascent methods, and they have completely different structure. So we have a function d, and we have a vector phi which you want to optimize over. The vector phi, that's a bit notation here, a bit messy, but yeah, I'll explain it. Yeah, what you do, your vector phi is of course a long vector with, as I said, million of variables. So you split it in blocks. On each step, elementary step of the algorithm, you optimize the function d with respect to a single block of these variables. So you find the optimum of this function with respect to, instead of optimizing with respect to million variables, you optimize with respect to 10 of them. Yeah? If you do it reasonably, you select the blocks reasonably, your function d, so your combinatorial problem and its relaxation is suitable. So you can do the optimization for all blocks in the same time as you do a single step of the subgradient. So it could be quite efficient. Unfortunately, on the theoretical side, it's everything bad. So this type of methods might get stuck arbitrarily far from the optimum. So you're not guaranteed to optimize the function at all. And moreover, in the case you have the number of blocks is more than n, you don't know in how fast it converges. At least theoretically, you don't know. There are no results, as far as I know. Why would you, if you see such things, you can ask yourself why would start working with this? Why would you consider that kind of methods? And basically, my next slides I will try to persuade you that it makes sense to consider them. Oh, okay. Here I have another outline of my talk. Now I believe now we can understand what's going on for them. So there are a number. As I said, I want to speak about fast solvers, and there are a number of features of a fast, efficient solver, and that's just 4 of these features. Update rule, which says basically whether you do subgradient based methods or you do block on descent, and if subgradient based, which of them, and block on descent also which of them. There are also a zoo of sub methods, so to say. Problem decomposition, in a sense, that's a way you can construct dual problems in different ways. I just have shown you a single one. Block of variables to optimize over. So if you decide for the block on descent method, you have to decide how you select the blocks you optimize over. Yeah? And of course, you want to build algorithms which are well parallelizable nowadays, at least. Well, I don't have unlimited time. You don't have. We also want to go for lunch or coffee break or whatever. Therefore, I have to concentrate on just 2 of these properties. Okay, but forget about disclaimer here. But first of all, I will show you. I try to show you the performance of the method on some data, and I also just select exemplary data. So one example from stereo construction, one example from bioimaging, whatever. And of course, it's not represented in any way. Just believe me that you get similar results on other data sets. I don't show it here. It's not comparison here in no way. I just believe me that it performs similar on other data sets, similar data sets. And another thing is all the data we have here for comparison have a common property that the unary costs, so the costs sitting in the labels, dominate the cost of the whole problem. So in a sense, if you remember what your neural network does, it actually produces the nice unaries, and that's what's the 99.99% of the world actually take as an output. So it's already not that bad. Yeah? You can do better, I've shown in the slide, but it's already not that bad. It's already quite close to what you actually would like to have. Good. So let's start with update rule. And we compare between subgradient-based and block on descent-based methods. Well, I probably have to do here some explanation. That's a serial construction problem. Tsukuba is already, I believe it's at least 20 years old, maybe more, even more. And as I said, don't look into particular examples. The result generalized to others. The plots we will have here, they show convergence of the dual problem. So that's some approximation of your problem. Again, believe me that the higher the curve here, the better the results in the application. I don't show you here. I won't show you the stereo construction, just because for stereo I could show it, but for some other results it will be just building such a visualization is the work on itself. You know. I'm interested in these curves, so I'm interested in the highest curve on this plot. You also see here that some numbers they basically say it's higher or lower. It's enough to know what that. And here you see oracle calls. If you don't know that, you can think about iteration of the method under the construction, under the disclaimer that iterations are comparable in time. Yeah? But in a sense, that's a number of elementary operations which are different methods are the same, but you build different methods with these elementary operations. Yeah? Good. So what you see here, we see that block on descent method basically performs all others. Bundle, smoothing plus accelerated gradient, ADMS, prox-based methods. So all those guys are worse, significantly worse than block on descent. Another example is color segmentation. It's example, you have an image, you want to approximate this 16 millions of colors with say 12 colors for some reasons. And you can build the corresponding discrete energy minimization problem for that. Want to solve it. Again, the gap between block on descent and other methods is not that big, but it's still the best one. Protein folding, one of the classical methods from again 80s probably. Here for this optimization problem, again block on descent wins. the competition. Worm reconstruction, that's a problem I presented at the very first slide of the title. I don't have other methods here, they are just much worse. So block on descent is the winner. So why? So basically, in all data sets I have here, the block on descent methods are the practically the fastest. Why it's like that? Again, I have to do some trade-off between the complexity of my explanation and the understandability. That it's understandable, still understandable. So if you think about computing subgradient of these problems, the subgradient, it turns out that the subgradient is just a vector as long as the vector of the dual variables. So it's like have 1 million of coordinates, think of that. And these coordinates, these numbers are sitting here exactly say, on the pairwise costs. Yeah? This red curves here denote a single number. Yeah? So you have basically for a given node and a given edge, so pairwise factor, you have as many dual variables and as many coordinates of subgradient as many labels you have. It turns out that in the subgradient you have exactly at most two coordinates which are non-zero. The one which correspond to the locally optimal label, and the one which correspond to the locally optimal label corresponding to the local optimal label pair, so the local optimal edge. So these two red ones are non-zero, all other are zeros. Think about stereo reconstruction problem when you have hundreds of labels, and then the two coordinates are non-zero. So what you do in your subgradient method, on each iteration you update only two numbers out of 100. So to update all 100 numbers, roughly speaking, you need 50 iterations. Yeah. If you are familiar with this generalization of the subgradient method with all these procs and smoothing and whatever techniques, you may object me, say no, but there are other numbers that are also non-zero, and the answer is they are non-zero, but not far away from zero. They are not big enough, so to say. So in a nutshell, you optimize still just these two variables. Without going to technical details, what you do in the block coordinate set, by definition, you optimize with respect to all variables. So in a sense, you optimize with all these guys, seeing with all 100 variables at once. It turns out to be easy, depending how you select the blocks, but you can do it in a very efficient manner. So that's an explanation why these methods, which don't have really a nice theoretical ground, where theory says, well, they can deliver whatever bad results, perform very well in practice. Well, that's kind of small take-home message. Use a block coordinate descent if your subgradient of your problem is sparse. The second block, and I have around 20 minutes. Yeah? That's good. The second block of my talk is a block of variables to optimize over. We decided we do a block on descent, so now we have to select the block of variables. And there are in literature there are basically roughly speaking, three types of algorithms which you can classify how they select the block of variables to optimize over. One type of algorithms, I call them node-wise update. That's a mean-sum diffusion due to Professor Schlesinger and colleagues from 70s. Among those methods, the most well-performing in so-called TWS, so tree-weighted sequential message passing, due to Vladimir Kolmogorov from 2005. And that's actually, till, say, a couple of years, it was the method to use for solving this kind of problem. It was the method. So what it does, it optimizes the dual function which we considered so far with respect to variables which are in a sense attached to a given node. So all these arcs here correspond to a single number, to a single dual variable, and you optimize for all numbers which are attached to the labels of a given node. Optimize at once in one elementary step. And then you go to another node in a certain order, and you obtain quite fast convergence and quite reasonable results. Second type are edgewise updates, where the variables optimize, those variables optimize which are attached to a given edge of the graph. Yeah, that's all these red arcs. The most prominent solver to say is MPLP from 2008 from Amir Globerson, and MPLP++ from our lab. Yeah, okay. I have here the bold setting is just saying the methods which I'll show you then on the plots, and the methods which I perform much better. So this algorithm differs from this one in one line of code, and is around 30 to 50 times faster. So I'm saying the block of variables update doesn't say you precisely the algorithm, but it gives you some feature which is important. And chain-wise updates, where you select the chain from the graph, so some subgraph which has a chain structure, and optimize over variables which belongs to this chain, basically. Probably one of the first algorithms in this direction was due to David Sonntag, 2009, so-called tree-block coordinate descent, which was already at that time much slower than this one. And the next algorithm, due to Savchynskyy 2016, is already much faster than this one. And so this one use the same updates as this same block of variables, but different update rules, is kind of 100 times faster than this. Again, the same setting. The plots look slightly different because they were generated just a couple of days ago by my PhD student. And so, who is who here? The green line, okay, the blue line is TWS. It's node-wise update. That's the state-of-the-art solver, which was a long time the solver for this problem. The red curve is the chain-wise updates due to Alex Rousseau. On this curve, it's slightly faster than this one. And the green one is the edge-wise updates, so-called MPLP++. So recall what we have. We have a sparse grid graph. Again, very similar problem, sparse grid graph. That's a key property here. We have, again, basically the same order. The chain-wise updates are the fastest, then are followed by node-wise updates by TWS, and the slowest method corresponds to the edge-wise updates. The picture rapidly changes. It changes completely if you consider the densely connected graphs. It's pretty unfolding, fully connected graph, much smaller number of nodes, much larger number of labels, but important is the fully connected graph. Here, the edge-wise updates suddenly beat all other methods you've seen so far, and they're followed by chain-wise and the state-of-the-art TWS. The same picture is repeated by others, fully connected models, full graphs, 6-depose estimation, worm. It's not fully connected, but quite dense. Oops. Good. So you have a couple of grid graphs, a couple of dense, fully connected graphs. The take-home messages here are the edge or chain-wise updates are more efficient than node-wise. And that's the take-home message. I say a few words about that. And basically use chain-wise updates for sparse graph and edge-wise for dense ones. This message probably requires some explanation. Why it's like that? Why it's not on? Why do we think it performs like that? And the explanation is following if you have a sparse graph, you change the solution in one part of the graph, and you have to propagate this information to another part of the graph. Due to chains, you can do the propagation just in one iteration. If you consider very local updates like node-wise or edge-wise, you need multiple iterations to do this to perform this update. If your graph is densely connected, so basically each node of the graph is connected to all others in 1-2 steps, you don't need long chains to propagate the information. You can do it directly, so edge-wise updates perform well. But now you might say, well, but why it harms to use the chain-wise updates for densely connected graphs? And the answer is the the computational cost to compute the update for the chain grows super linearly. So it's like something like n log n. Therefore, if you take longer chains, you pay the price for that. Therefore, iteration-wise, the method would perform similarly, but if you compute really the time you need to do that, it's getting slower. Oh. Actually, I'm kind of done with my talk. I have 3 bonus slides, which are, yeah? Okay, I'll show you the 3 bonus slides. Yeah. What we are working on. We are working on parallelization, of course, of parallel algorithms to make them even faster. And that's kind of how the life changed 2018 when we published we published the MPLP++ algorithm. I'm not sure that you can see here, so therefore I will basically say it. So this blue bar, that's a time. Forget about numbers here. Hopefully you don't see them. Just everything relatively. So that's a blue bar. That's a time needed for the TWS. So the long time the method, the state of that method for solving up to a certain precision our dual problem. This green bar is a single core variant. This green bar is a single core MPLP++, so the winner for dense models, and that's a 4-core variant of that. So you see that that's a jump like in the last couple of years in performance. Basically, the picture looks very similar for 3 densely connected types of problems. If you now get back to the grid graphs, which still are quite useful in computer vision, can be quite useful. The picture is just getting it's everything upside down. So this is still the long time winner TWS, and it's our method with 4 cores. It doesn't look very promising, and our current work, which is basically getting the same picture as for dense graph for grid graphs and any sparse graphs as well. So basically for any neighborhood structure of the graph. Second bonus slide is cell tracking problem. It's very related to the things I was speaking about. So what you do, you have a raw data images. You, as I said, you generate over segmentations to generate multiple segment hypotheses, and then you try to build a consistent picture out of this cell hypothesis to give to obtain the so-called lineage tree. So to know which part of the living being comes from which cell, which cell comes. So there are a couple of groups in the world which work on this problem, and if you look into what kind of solvers they use, they either use quite heuristical solvers where you don't really know how to perform if you give another data to that. So it's hard to predict what they're doing, and or they formulate the problem as integer linear program and then run the standard Gorobi or CPLX solver for that. And this plot and we basically have here 2 curves. Our curve, so the dual and the primal solution, and the Gorobi result. So our solver gives approximate result, and it's already useful somewhere here. So after half a minute or 1 minute of the time, whereas Gorobi requires, say, 6-8 minutes. You might say, well, 6-8 minutes. We train our networks now 6-8 weeks. But it depends again on the situation, what you are going to do here. And if you imagine you're a biologist, you have an image of the cells. You press a button and go to drink coffee. 6 minutes, it's not that bad. It's enough to drink a coffee. You come back, you have a solution, and then you realize, well, here I want to correct something here. You press the button, say that this cell is incorrect, so correct. Could you please recompute it? Yeah, and now you imagine you have to click not once, but 100 times, and it's getting a mess. You're not going to work with the program which requires each time you click a button requires 6 minutes. Therefore, what you want, of course, you want to be able to recompute the solutions as fast as possible. And there's another, the third bonus slide. So far, I was speaking about approximate solvers for all this kind of problems. But it turns out that if you do it long enough, you realize the problems which come from the real world, from computer vision, they're actually quite simple, even if they are NP-hard in a very general setting. And what you see here, so you probably, on some images at least, you see the red blobs here. What does it mean? If you recall at the very beginning, I have shown you how to build what is a Lagrange dual, and it says it was select in each pixel the optimal label, and in each pair of pixels the optimal label pair. And so everywhere without red color, actually these selected pixels and label pair are consistent after solving the dual problem. If you don't solve it, it's not consistent at all, it's just math here. But if you solve it approximately, it's almost everywhere consistent, except in these red areas or even smaller areas. And using this fact, they are almost everywhere consistent. So optimization, people say that the approximation is almost tight here. It turns out you can solve this huge problems with millions of variables exactly in a quite, for optimization, very small time. If you're interested in exact solution, if you're a mathematician. And just to give you an idea what does it mean, so CPLX is a commercial integer linear program solver. They have like 30 data sets of the worm, 30 instances of the worm. It's able, within a half an hour, it's able to solve one of them. Oh, no, within an hour. Okay, that's 45 minutes. 54 minutes, sorry, I lived too long in Germany. 55 minutes, which requires to solve this single instance. That's a specialized toolbar to its competitor, which is a specialized solver for discrete graphical models, exact solver. It's able to solve exactly 13 instances within an hour, and requires, say, about 8 minutes per instance in average. And that's our results. We are able to solve 25 out of 30, and require even less time per instance than this one. So, you're not allowed to compare this number with this one, because among these 25 are also 10 those where this solver require more than an hour. You know, and we are still able to solve them in average in less than 6 minutes. Well. Take-home message in future work. Yeah? Block coordinate descent is a nice, so it's preferable with subgradient sparse. Use it. If you have a long-range interaction, it means you have a sparse graph where the solution, one part of the graph depends on the solution other part. Use the chain-wise updates on more general. Use the larger subgraphs to update the dual variables. And chain-wise or edge-wise updates are more efficient than node-wise ones, so they can be made more efficient. Which depends on the details, which I didn't cover here. We are working on parallelizable decomposition-based so methods so basically chain-wise updates or tree-based updates for general graphs and more general problems which are beyond the discrete graphical models I've spoken about. And the very last slide, was thank you for your attention, yeah, and thank you for your patience. Recently, I basically submitted a textbook about discrete graphical models. So if you know to learn more background in this area, I'm interested in the number of people able to solve this kind of problems efficiently, getting more than just a few in the world. Therefore, I wrote a book about that, and read the book. It's freely available in the web. Thank you for your attention.
Thank you, Bogdan. Okay, we have time just for 5 questions, so please.
Hi, thank you for the talk. I have just some several questions, but I'll just keep it to 2 maybe. So regarding this using block coordinate descent compared to subgradient, I think this is